Let's talk about a proposition. Let A and B be non-zero vectors in R3, and theta be the angle between A and B. Then, the length of A cross B equals the length of A times the length of B times sine theta, which is equal to the area of the parallelogram formed by A and B. To prove this result, let A be the vector A1, A2, A3, and B be the vector B1, B2, B3. We consider the square of the expression the length of A times the length of B times sine theta. This equals the length of A squared times the length of B squared times 1 minus cos squared theta. This equals the length of A squared times the length of B squared minus the square of A dot B, where we have used a property of the dot product, which states that A dot B equals the length of A times the length of B times cos theta. Applying the definitions, this equals bracket A1 squared plus A2 squared plus A3 squared times bracket B1 squared plus B2 squared plus B3 squared minus the square of A1 B1 plus A2 B2 plus A3 B3. Expanding the brackets, we have A2 squared B3 squared plus A3 squared B2 squared plus A3 squared B1 squared plus A1 squared B3 squared plus A1 squared B2 squared plus A2 squared B1 squared minus 2A1 B1 A2 B2 minus 2A2 B2 A3 B3 minus 2A1 B1 A3 B3. Regrouping the terms, we have the square of A2 B3 minus A3 B2 plus the square of A3 B1 minus A1 B3 plus the square of A1 B2 minus A2 B1, and this is equal to the square of length of A cross B. Hence, the length of A cross B equals the length of A times the length of B times sine theta. Now we consider the parallelogram formed by A and B. By taking the length of B as the base, we know that the height is equal to the length of A times sine theta using simple trigonometry. Hence, the area of the parallelogram equals the length of B times the length of A times sine theta, which equals the length of A times the length of B times sine theta. And this completes the proof. Let's look at a corollary of this result. Let A and B be non-zero vectors in R3. Then A cross B equals the zero vector if and only if A and B are parallel. For the proof, A cross B equals the zero vector if and only if the length of A cross B equals 0. From the previous result, this happens if and only if the length of A times the length of B times sine theta equals 0. Since the length of A and the length of B are non-zero, this happens if and only if theta equals 0. In other words, A and B are parallel. Let's look at an example. Suppose we want to find the area of the triangle in R3 with vertices 1, 0, 0, 1, 1, 0, and 0, 1, 1. Let A be the vector 1, 1, 0 minus 1, 0, 0, which equals 0, 1, 0. Let B be the vector 0, 1, 1 minus 1, 0, 0, which equals negative 1, 1, 1. Note that the lengths of these two vectors are equal to the lengths of two sides of the triangle. To find the area of the triangle, it suffices to find the area of the parallelogram formed by A and B and divide by 2, which in turn can be found by computing the cross product of A and B. So we compute A cross B equals the determinant of E1, E2, E3, 0, 1, 0, negative 1, 1, 1. This equals the vector 1, 0, 1. Hence, the area of the triangle is equal to 1/2 times the area of the parallelogram formed by A and B, which equals 1/2 times the length of A cross B. This equals to 1/2 times the square root of 1 squared plus 0 squared plus 1 squared, and we get the answer square root of 2 over 2. Now, let's consider vectors A, B, C in R3, which do not lie on the same plane. They determine a solid called a parallelepiped. It has 6 faces, each of which is a parallelogram. This is a generalization of the fact that two vectors form a parallelogram. Let's look at a proposition. Let A, B, C be vectors in R3 which do not lie on the same plane. The volume of the parallelepiped formed by A, B, and C is equal to the absolute value of A dot bracket B cross C. For the proof, let n be a normal vector to the plane containing A, B, and C. Let theta be the angle between A and n. We know that B cross C is perpendicular to B and C, and also n is perpendicular to B and C. So, n is parallel to B cross C, and the angle between A and B cross C is phi, which is either theta or 180 degrees minus theta. Now, the volume of the parallelepiped is equal to the base area times the height, where the base area is the area of the parallelogram formed by B and C, which is the length of B cross C, and the height is equal to the length of A times cos theta. Since cos of 180 degrees minus theta equals negative cos theta, we can rewrite cos theta as the absolute value of cos phi, because cos phi is equal to cos theta or negative cos theta. So the expression becomes the length of A times the length of B cross C times the absolute value of cos phi. This is exactly equal to the absolute value of A dot bracket B cross C, and this completes the proof. Now, let's talk about some properties of the scalar triple product. For any vectors A, B, and C in R3, A dot B cross C equals C dot A cross B equals B dot C cross A. We write A dot B cross C equals the determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3. We swap the second and the third rows to give the negative of the determinant A1, A2, A3, C1, C2, C3, B1, B2, B3. Now we've swapped the first and the second rows to give the determinant of C1, C2, C3, A1, A2, A3, B1, B2, B3, which is equal to C dot A cross B. Similarly, by swapping two rows of the determinant twice, we have C dot A cross B equals B dot C cross A. The second property, A, B, and C are coplanar, in other words, lying on the same plane, if and only if A dot B cross C equals 0. Indeed, A, B, and C are coplanar if and only if the volume of the parallelepiped formed by A, B, and C is 0. Using the previous result, this happens if and only if A dot B cross C equals 0. Alternatively, we can prove the second property as follows. A, B, and C are coplanar if and only if there exists a vector n in the form n1, n2, n3 which is non-zero, such that A dot n equals B dot n equals C dot n equals 0. Here, n is a normal vector to the plane containing A, B, and C. This happens if and only if the homogeneous system A1, A2, A3, B1, B2, B3, C1, C2, C3 times n1, n2, n3 equals the zero vector has a non-trivial solution. This happens if and only if the determinant of the coefficient matrix A1, A2, A3, B1, B2, B3, C1, C2, C3 is 0, which in turn happens if and only if A dot B cross C equals 0. Let's look at an example. Suppose we want to determine whether the points 1, 0, 0, 1, 1, 1, 1, 2, 3, and 2, 3, 4 are coplanar. Let A equals 1, 1, 1 minus 1, 0, 0, which equals 0, 1, 1. B equals 1, 2, 3 minus 1, 0, 0, which equals 0, 2, 3. C equals 2, 3, 4 minus 1, 0, 0, equals 1, 3, 4. These three vectors, originating from the same point, form a parallelepiped, and its volume tells us whether the 4 points are coplanar. So we compute A dot B cross C, which equals the determinant of 0, 1, 1, 0, 2, 3, 1, 3, 4. Expanding along the first column, we get 1 times the determinant 1, 1, 2, 3. This equals 1, which is non-zero. So the volume of the parallelepiped formed by A, B, and C is non-zero, which means that the 4 points are not coplanar. Given 3 vectors A, B, and C in R3, what is bracket A cross B cross C? We know that bracket A cross B cross C is a vector perpendicular to A cross B, while A cross B is perpendicular to both A and B. Hence, bracket A cross B cross C is parallel to the plane containing A and B. In other words, bracket A cross B cross C lies on a plane containing A and B. The following proposition gives the exact expression of this vector. For any vectors A, B, and C in R3, bracket A cross B cross C equals bracket A dot C times B minus bracket B dot C times A. We let A equals A1, A2, A3, B equals B1, B2, B3, and C equals C1, C2, C3. A cross B equals the vector A2, B3 minus A3, B2, A3, B1 minus A1, B3, A1, B2 minus A2, B1. Now, the x1 coordinate of bracket A cross B cross C equals bracket A3, B1 minus A1, B3 times C3 minus bracket A1, B2 minus A2, B1 times C2. This equals A3, B1, C3 minus A1, B3, C3 minus A1, B2, C2 plus A2, B1, C2. On the other hand, the x1 coordinate of bracket A dot C times B minus bracket B dot C times A equals bracket A1, C1 plus A2, C2 plus A3, C3 times B1 minus bracket B1, C1 plus B2, C2 plus B3, C3 times A1. This equals A1, B1, C1 plus A2, B1, C2 plus A3, B1, C3 minus A1, B1, C1 minus A1, B2, C2 minus A1, B3, C3. This equals A3, B1, C3 minus A1, B3, C3 minus A1, B2, C2 plus A2, B1, C2. So the two expressions are equal. Similarly, the expressions for the x2 coordinates and x3 coordinates are equal, so the two vectors are equal. Secondly, A cross bracket B cross C equals bracket A dot C times B minus bracket A dot B times C. We can make use of the first point and the properties of the vector product to prove this result more quickly. A cross bracket B cross C equals the negative of the vector bracket B cross C cross A. This equals the vector negative B cross C cross A. This equals bracket C cross B cross A. Using the first point, this equals bracket C dot A times B minus bracket B dot A times C. Finally, we can swap the two vectors in the dot products to give bracket A dot C times B minus bracket A dot B times C, and this completes the proof.